Cool. Okay, so again, welcome everyone to Paper Club. This week, Inneke is going to present. Inneke is our most recently joined machine learning engineer. And she found this interesting paper about transformers and how to address one of the biggest problems in transformers, which is the training time. And it's a very interesting approach on how to progressively change layers in the transformers to make the training a lot faster. So it should be very interesting. Go for it.
Okay, hello everyone. So I'm going to share my screen. Okay. Can you see my screen?
Yep.
Okay, it's this one. All right. Okay. Yeah. Today we're going to discuss about this paper called Accelerating Training of Transformer-Based Language Models with Progressive Layer Dropping. I find this paper interesting because it addresses the problem that many of us have faced when training transformer-based models, which is it is very computationally expensive and the training time is so slow. And another thing that I find interesting is that their approach to address this problem is not by adding more hardware, but they change the training what they call the training algorithm by dropping some layers. So it's very interesting because I think it's also very doable for most of us who don't have access to fancy hardwares. Okay, so as we know that with the challenge of training transformer networks, this paper first explains about some of the previous approaches to solve this problem. The first one is mixed precision training. This is a way of training where we use, instead of the 32-bit floating points, mixed precision training use the 16-bit. So the problem that mixed precision training is trying to solve is to make our memory consumption is less by using a smaller floating point. But it also has its drawback where it requires the tensor cores. So it's not always accessible by a lot of people. The second point about solving this transformer problem is by doing distributed training. But actually, again, it will lead to parallelism, which might converge to not to the global minima, but to the local minima, and generalization is poor. The other approach that people have tried is by using something called LAM, which is a layer-wise adaptive large batch optimizer. But again, this also requires a lot of hardware, thousands of GPUs, which is not always accessible also for most of the people. What this paper is trying to do is by looking at different architecture of transformer, which is very interesting. One of the technique that actually inspires this paper is a training algorithm called Stochastic Depth, which is something that people have used earlier in image recognition training. Before we go deeper in this paper, I think it's good for us to take a look at this stochastic depth, because actually it's this paper is doing something similar to stochastic depth, but with a more advancement. So what is training with stochastic depth? the problem that stochastic depth is trying to solve is the dilemma when we train a big model, where if we use a big model for training, we can have a vanishing gradient problems, or the training time is so slow. But on the other hand, we cannot use too small model for training, because the model might not be able to learn the features in our data. So what stochastic depth does is that we use a smaller model during the training time, and then we use a full-time model during the inference time. So this way, we hope we can have the maximum performance of a model, but we can avoid the problems with vanishing gradients or slow training time. So if we look at, there is a illustration in this paper, so I think that one really explains what is actually happening. Yeah, originally this paper is done in the ResNet block, in a ResNet architecture. So during the training, we will drop this ResNet. Okay, this one is the illustration that I think really explains what actually stochastic depth does. So in this algorithm, we want to drop the ResNet blocks along the depth dimension of our model. So we see in the earlier layer, we keep all of the ResNet blocks, and then along the depth, along the depth dimension of the model, we will drop more and more layers. This way, we are hoping that during the training, the model will be smaller, but then when doing the inference, we will use the whole architecture of the model, and we don't drop any layers. So they also add. There's also a reason why we prefer to drop the deeper layers compared to the earlier layers, because we believe that the earlier layers are very necessary to extract more features than the later layers. So that's why we cannot remove the earlier layers. So yeah, that's a little bit of stochastic depth. So it's basically a dropping ResNet blocks in terms of depth dimension. And then back to our paper, we will see this author says that actually implementing stochastic depth only will harm the performance of transformers. And this is one thing that also this paper trying to discuss, why doing this stochastic depth will not work in transformer and what can we do with it. The first contribution of this paper, first, we will see what's wrong with the stochastic depth in this transformer. And then secondly, they introduce something called switchable transformer block. And then the third point is we're going to add a progressive schedule. So in addition to the depth dimension dropping in stochastic depth, here we also have a dropping in terms of a temporal schedule. And the last point, we will prove here that even though we have a smaller model, it will not hurt the performance. Okay, so the next part of the paper, we're going to see I think it's better for us to just look at the image. In the image, in the figure 6. Yeah, we will see that actually this is the number of floating point operations per training iteration normalized to the baseline. So we will see that along the training steps, so in the temporal dimension, we can see that actually we can optimize the training in the later time compared to the earlier time. So this is a basis of the temporal schedule that they mentioned in this paper. Okay, and we will just see that another statement that they have here is that they also tried training bird with a smaller depth, but then unfortunately it hurts the model performance even though they used knowledge distillation. So it means that for transformer-based model, actually by simply removing layers, it's not a good idea because we will sacrifice a lot of performance. Okay, then we will go next to the next section. Okay, this section also introduced us to a modified transformer layer. So the original transformer is using post-LN. LN here stands for layer normalization. What does post-LN mean? It means that the layer normalization blocks is positioned after the residual blocks, like the identity mapping in transformer. To make it easier for us to visualize it, we will going to look at the original paper that introduced this. So the left figure is the original transformer architecture, where we see the layer normalization is positioned after the identity mapping part here, and also the same pattern here. And what pre-LN offers, actually we move the layer normalization inside the residual part here. So instead of doing it after the addition layer here, we do it before the attention. Why this paper proposed this new transformer architecture? We can see here that they claim the study that they do in this paper saying that by using this new pre-LN architecture, we can get rid of unstable training, and also we can get rid of the warm up section before the training. So normally when we train the transformer, we need to use a warm up period, which means that we start with very low learning rate, and then either we gradually increase the learning rate or we change the learning rate to the normal learning rate we want, which actually that might lead to slower training because we need to start slow. In this paper, they claim that by changing the architecture by moving the LN layer in the residual section, we can get rid of that problem, and we can start our training with the normal learning rate without using the warm-up section, and also leads to more stable training. So this is the reason. Let's go back to our original paper. This is the reason why in this paper they used to they choose to use the pre-LN instead of the post-LN. Okay. They also have they did a small study to compare the pre-LN versus post-LN that we can see here. The first two figures shows the cosine similarity, the L2 norm of the input and output embeddings in the earlier step, in the earlier time of the training. And then the other two figures shows the the L2 norm and the constant similarity in the later part of the training. And then we can see here actually in the later part of the training, okay, the x-axis is the layer, is the depth dimension of the model. We can see that with the deeper layer, one thing is that because here they used the arc cosine, so the lower the number, the more similar the two inputs. So we can see here that along the with the deeper layer, actually we have a more similarity, and then the L2 and constant similarity looks they have a similar trend compared to the first image, the first figure, which is the earlier steps of the training. So we can say that in the earlier step of the training, actually the model is still trying to adjusting the weights, still to understand the features, and then later, in the later step of training, the model starts to stabilize, and here this time we can drop more layers. So that's the basic idea of this paper. Okay. And also we can see that they also did a study that if we remove layers in post-LN instead of pre-LN, it will significantly reduce the performance. And also in the diverged training, we can see in the figure 3. We can see here that the lowest loss we can get from the pre-LN, and then when we add a dropping to the layers, the pre-LN is like the change is not as significant as compared to if we drop the layers in post-LN, which means we should go for pre-LN in this paper. Okay, and then we go to the new idea that they proposed here. They introduced a new block called switchable transformer blocks. The figure here really illustrates what is happening actually. So we see in the first figure, this is the original transformer layer with the post-LN, and then the second figure is the pre-LN transformer, and then the third figure is the one that they propose, which actually adding a gate. Here they call it G. So the use of this gate is that we can switch on or off the gate, which means when we switch off the gate, we drop the layers. Okay, so, and this is how we're going to remove or drop the layers. We're going to, as we see in a one single block, there are two gates here, but in this paper, we will use the same value of G. So if G is equal to 1, it means that these two will be kept, will be retained, and if we use G is equal to 0, means both of these will be dropped. Okay, and here we also see that how we find G actually is a Bernoulli random variable where P is the probability of retaining that layer. And same with the idea of stochastic depth. Later during the inference time, we're going to scale back the model with the scaling factor 1 over the P2 because we want to use the full model for the inference. Okay, the next step of this paper is discussing about how we're going to make the heuristic of the dropping schedule. We can see here that they use basically the layer dropping will only increase along the tremble dimension, which means as we look at the previous study that in the aerial step of training, the model is still adjusting the weights, and then the later step of the training, the models try to stabilize and then start to like understand the features. So this means that we don't want to drop layers in the earlier time of training. We only want to drop in the later time of training. It means we will increase the probability of dropping layers along the time. And they use here, yeah, okay. So this is the heuristic that they used to define the probability of the number of retained layers. In the first step, where t is 0, we're going to retain all the layers, and then after that, the layer is gradually dropped until we reach theta bar at the end of our training steps. Here they also use this heuristics where gamma is 100/t, which, to be honest, I'm not really sure like why they choose this one. So if anyone have an idea the reason why they use this gamma number, because I don't think they do ablation studies with this heuristic. So I'm not really sure what's the impact of this gamma number.
Yeah, well, from what I understand, they're not actually using the. So they're using an approximate schedule to turn off the layers. So they're not using the correct like the formal definition of schedule, and they pick that. So the end value. So it says right after that the error is small. So the error in estimating the correct probability of keeping layers is very small. But yeah, I don't think there's any more motivation around it.
Yeah.
They just assume that you have a lot of epochs to work with.
Yes, exactly. They made the assumption here. Okay. The next part of this paper, they introduce the dropping along the depth dimension, which actually is similar to that stochastic depth idea. Instead of dropping the same number of layers for each step, we want to also gradually drop the layers along the dimension. The idea is inspired the stochastic depth. That's because in the earlier layers, the model will need the full layers because the model is still trying to understand the low level features. But along the depth dimension, we can make it more efficient because actually the features already run, and we don't need the full capacity of the model. So if we look here, instead of using the same probability of layer retaining, they introduce another heuristic here, which actually is just a linear formula to drop the layers. I think it's also worth to look at these pseudocodes. I find it more clear to understand what they are trying to do. So yeah, if we have a T number of steps of our training, we're going to start with actually we're not going to drop any layers in the first T, and we aim to have a theta bar value at the end of the training, and then for each layer in the depth dimension, we're going to take a Bernoulli random variable to know the number of layers that we're going to drop. Sorry, to see for each layer like how many layers we're going to retain. Okay. So yeah, basically that's the idea that they proposed in this paper. And they also say that here, yeah, basically if we drop the layers, we're not going to perform forward and backward computations because it's just because the layer is bypassed. So yeah, that they will definitely shorten the training time. Okay. Yeah, the next section is we're going to see how this new architecture performs. So for the data set, you're going to also use glue as a benchmark. And they use the bird model from hiking phase. And then they have 186 epoch. Something interesting is that they still use a warm-up ratio of learning rate, which actually in the pre-LN versus post-LN paper, they claim by using pre-LN, they can get rid of a warm-up stage. But here they still use the warm-up stage anyway. And yeah, the bird has 12 layers. Okay. Let's see the results of the training. The first one, we can see at figure 7a. Figure 7a. You can see here that PLD is the new algorithm progressive layer dropping. We can see that actually with the same learning rate, our PLD actually can reach the baseline. Sorry, this one. The blue line is the high learning rate. Okay, with the smaller learning rate, you can achieve the same performance, the validation loss with the baseline, which means we don't hurt the performance of the model. And we can also see that with the baseline model, when we use a higher learning rate, the model diverges, while using PLD, the model doesn't diverge, which is also another plus point of this new PLD. The next thing is the speed. We can see in the figure 7b that using the PLD, it leads to a more stable training, where we can see that it converges faster than the baseline. And we can see here they claim that the speed gain we have is 2.8 faster than the baseline. Okay, yeah. Also using the fewer training samples. So it reached the same loss at the epoch 87 with a few training example. After that, they also compare the results in the drawstring task using a glue benchmark. Let's see here in the table. In the table, we can see that this is the bird original with the baseline. Okay, with the baseline bird in the epoch 186, we can reach a better performance from 82.1 to 83.2. While actually, even in the epoch 100, we already outperforms the baseline bird. So definitely it leads to faster training. We don't need to train until 186 to reach the same performance. Okay. Oh, right. And then, yep, basically that's all. And then the last part is the ablation studies. They try to train the model with different learning rates, which is presented in figure 9. Okay, we will see that with the higher learning rates, okay, we can see the lighter color means lower learning rate, and the darker color means high learning rates. We can see here with the higher learning rate, the performance is way better compared to baseline. And this occurs in all of the datasets, all of the benchmark they use, which is really good. When using a small learning rate, actually the performance of PLD is worse compared to baseline, but when we increase learning rate, it will be way better. So yeah, it's very interesting. So the second ablation studies they did is the effect of theta bar. Theta bar is the final keep ratio we want to achieve, and the result is presented in figure 10. We will see that when we, okay, the worst performance happens when the theta bar is 0.3, means we only retain 30% of the layers, which leads to model divergence. But yeah, it's other than that, with 0.5 theta bar, the model is still converging. The third study is about PLD versus pre-LN. We will see that why using pre-LN only without PLD will not achieve the same performance as PLD. So there are experiments with a low learning rate that used to train post-LN, and the hyperparameters used for the PLD with this with high learning rate. And we can see also in the table 3. Okay, this is a lot of comparisons that they make. The part with the pre-LN with the same learning rate is actually performing worse than bird with post-LN. But when we use a higher learning rate, the performance is way better with 0.5 by 0.5%, which actually it supports the previous studies about using higher learning rate versus lower learning rate. Yes, the rest of the ablation studies is presented in this table. Another study they do is to compare also the use of PLD with the use of only dropping layers in depth dimension, which is the same with stochastic depth. They call it the random. So, and we can see by using the method of stochastic depth only, not using the temporal schedule, will also not lead to the best performance. The same case with comparing training it with temporal schedule only, using the same number of layer drop along the depth dimension, only using the temporal schedule, also leads to the not the best performance, which concludes that by combining this bird with pre-LN with high learning rate with the temporal schedule and also dropping layers in depth dimension, gives the best performance. And also, they also mention here when they train using the temporal dimension only, they have problem when they try to train with mixed precision. They don't really mention about this in the main study of this paper, but here they claim that they cannot use the half precision training and they need to use to switch to the full precision because the training diverge. Yeah, which means that it consumes more memory also. Okay, yep, that's all from this paper. So please, if there's any comment.
Yeah, I think it's a really cool paper. I had a couple of comments, and maybe if we can get the opinion of people attending as well, it would be cool. So the first comment is that in the original BERT paper, they actually say that they ran out, that they do not get better performance because they don't have any more resources. So this is actually, it's quite interesting that this paper shows that, well, in fact, if you are a bit smart about training these super massive models, you can actually squeeze more out of them, because it seems to say like, okay, we're still using this BERT architecture, but we're just training it smartly, so we can actually reach the performance that the original paper said they couldn't, because they don't have any more resources. So I think that's cool. The other comment that I had is that this form of layer dropping, it seems like a very aggressive dropout, right? So you're not just dropping random units, but you're dropping entire layers, which makes me think that BERT is over-parameterized, like heavily over-parameterized. And I don't know, I don't have a big idea about what that implies, but like, what do you think would be the implication? Like, can we make a smaller transformer-based models that would have the same impact, or is it just a matter of continuing doing these like different pathways of training?
I was thinking that we had this paper many years by now ago, where we talked about how these resonant layers are like a differential equation, right? Because the input and output have the same shape, and now you're essentially saying that you can sort of reduce your integration path, make it shorter or longer, and you would expect the same output. That to some extent means that the equations themselves must be invariant, meaning that no matter where in the path you go, you sort of do the same thing, and you just expect it to get better as the deeper you go. And I would imagine that this must also say something about the distribution of inputs to outputs, right? It must be some sort of self-similarity or so that is conserved there, but I have no idea how it would look in the mathematical form.
Yeah, well, I was actually thinking, because we've also had papers before that show how to efficiently navigate the loss landscape. So when you just said about this invariance of inputs, it makes me think that, well, yeah, the architecture is the same, all the targets are the same, but you're just providing it with a faster way of converging to a local minimum, which could be what this is doing.
Yeah, I mean, it's. Go ahead.
I was wondering, I was thinking about it a little bit differently, in terms of what it's learning at what layers during especially the pre-training aspect, right? Starting from random that we're doing here. And I thought it had a really nice kind of complementary relationship with this sort of differential learning rates that people use when training for a specific task, right? So where you hardly adjust the weights on the initial layers and do most of the learning at the the later layers. And so during pre-training, that's kind of flipped on its head, because all the interesting learning going on in pre-training is effectively in those first layers, whereas all the interesting training sort of subsequently for a specific task is happening in the later layers.
But so in that same like line of thought, so what would be the benefit of turning off? Oh, right, because the earlier layers are off with less probability.
Right.
But then what is the benefit of turning off with higher probability the later layers?
Because they're not contributing that much in those early phases of so when they're in a sense, they're learning rubbish because the early layers haven't settled in. And so the benefit is, primarily, you turn it, you just drop it out. It's not going to learn anything interesting in effect. So you're avoiding, learning things that turn out to be quite wrong because the early layers haven't settled. I guess early in that paper, they were saying, there are some folks who've already done just random dropout of the layers. And one of the awkwardnesses of doing that is sorry, I didn't mean random dropout. I mean, starting training the initial layers and then the next set and then the next set. And the awkwardness there is you don't really know how much training to do. And planning the overall sequence then becomes quite awkward unless you're doing this thing when you're repeating, BERT, where the kind of parameters are pretty well known, then you can use that approach to improve things. So I thought that fit pretty well with that kind of narrative that I'd constructed, at least in my head.
Yeah, that sounds very interesting. Cool.
Now, I don't know, they referenced a paper and I didn't follow up on it. And our speaker today, whose name I don't see in front of me, so I can't, sorry.
Inneke. Which paper? Which paper?
The one on sort of stochastic dropout in ResNets.
Yeah.
Yeah, what's the title of this paper? Stochastic Depth.
Yeah, so I hadn't seen that before. And so I wonder if effectively this technique applies, roughly speaking, both in ResNets and in the transformer environment, whether that really isn't suggesting there's something quite fundamental about it, especially in the pre-training context.
Well,
yeah, I think that's an interesting idea to keep doing research on. It's yeah.
That's one of these questions I ask myself about papers like this, right? Is there something really interesting and fundamental going on here, or is it something that we tick the box and say, wow, big improvement on training BERT, and it feels like, as you are linking it to dropout generally as a technique, which relate to normalization, regularization, normally is fundamentally as a technique, whether this kind of, really is starting to advance our knowledge of how to train, large, deep networks in a more sophisticated way.
Yeah. The reason I thought about dropout is so it's partially what you say, right? Like we have these massive models, and we see that by doing some very aggressive regularization, we can actually get them to learn more meaningful stuff and generalize better, which to me just says that we are over parameterizing our models. We're giving them too much capacity, and then we have to find clever ways to reduce that capacity.
But so I thought that was a stimulating and provocative statement, and I guess I thought possibly I might not agree with it in the following way. It's excess capacity when. So I don't know whether BERT overall is over-parameterized or not. But let's say, for the sake of it, that at the end, sort of in the end game, it's not over-parameterized. But when you're starting to learn, in effect, it is, because you haven't learned the basics yet. And that's kind of an interesting sort of, feels like a kind of entertaining way of thinking about it as well. You know, what's the sort of is the parameterization appropriate for the current aspect of your learning and task?
That's really interesting, because it would imply that you need to change the capacity as the model learns. You need to change capacity for it to generalize well.
Right, and that's effectively what these guys are doing in a kind of funny stochastic fashion.
Yeah, I think maybe one other point of view would be having the different length scales in there, that it occasionally helps to just have a shorter network for the information flow. Right, when I remember we had this paper about how easy it is for information to flow through your deep network. Now here it might not make sense, right? Because of these ResNet architectures, you always have essentially a free channel from beginning to end. But there might be a case to be made that's saying that, okay, if you drop the latter layers, the network essentially becomes shorter, and we have a stronger information flow through any particular unit that is maybe somewhere in the middle or at the beginning. Not sure whether that would held up to a rigorous examination, though.
Yeah, very interesting ideas. Maybe someone can write a research grant about it, and we can all work on it together. Cool. Are there any more questions or comments? Nope. Okay. Well, with that, thank you very much, Inneke. This was a really interesting discussion, sparked by a very interesting paper. As usual, please do get in touch with us if you want a paper to be discussed, or if you want a topic. If you have a topic in mind, we'll be more than happy to start talking about different topics in machine learning. We speak a lot about language models because at nPlan we care a lot about language models, so we read a lot about them. But we are open to different things. So if you find an interesting paper in any area of machine learning, please do send it our way, and we'll make sure that there's a discussion around it. We are currently expanding at nPlan. So if you know anyone interested in machine learning, data science, software engineering in general, please do send them our way. You can find all the open positions at nplan.io. I'll just launch a quick poll now. Cool. And yeah, thank you very much, Inneke. If we can show appreciation with a show of hands, that would be great.
Thank you very much. It was great.
And yeah, hope to see you in the next paper club.
Great. Thanks so much.
Thank you, everyone.